Hey guys, good morning. And I will be having an interesting, I will sharing an interesting idea with you on time series analysis. So the first part of this time series analysis will be about um, understanding. We'll be about understanding how the time series, how the whole thing develops. Okay, and what are the where we focus and why we learn what we learn. Okay, so that should be my first aim and first piece of content for you on time series. Okay, let's get started, guys. So if you look into the time series, in this video we'll be discussing about this following questions: that what is time series analysis, like what is time series, what exactly is the mathematics of time series, then like what is the probabilistic aspect of time series, then we will understand what is the main focus of time series, what we want to do in time series, and then we will learn how is time series really different from regression. You must have understood, like maybe you have learned time series or maybe you're learning time series. Time series is just a relationship between a variable and a time. Okay, so we'll understand how it's different from regression, and since it's different from regression, how to mathematically model it. Okay, and not only we will discuss what is different from regression, we'll also understand what is similarity with regression. And then there's an important condition called stationarity in time series. We'll also understand that, and then we'll also understand what is the central idea of time series, like if you want to just go to the point directly. And finally, the second part of the series is about AR and AMA and ARIMA modeling. So we'll learn how, like what is ARIMA modeling in short after all this. Okay, so I hope you will get a clear guide on what, like in the direction of why we think about what we think and do. So let's get started, guys. So let's understand. Oops. So here's some. I will just clear it up. Can we just clear it up? Just yeah, I think, yeah, perfectly. Okay, so now understand this, that time series. So let's go into what time series is all about. Okay, so time series is a data. So it's sort of, I'm using my Medium Walla blog as a presentation for you. So I will give the link of the Medium Walla blog so that you can read and like look into the video at the same time. So understand what is time series. A time series is a data. So if you try to understand time series, if you have let's say you have you're understanding your scores over a time, or maybe your blood pressure over time, or whatever you're looking forward to. So all are variables. Okay, x1, x2, xn, and this indexing 1 2 dot dot n, this indexing 1 2 dot dot n are actually time. So these data points are our discrete time, and for example, if you see it over here, this is actually a time series analysis, and maybe it's dependent on, it's, you can understand, it's like, it looks like a stock market, anything like looks very jagged, and we'll understand why it looks very jagged. Okay, why, what is the reason, it's the reason behind it's looking very jagged. Okay, so we'll understand that, and this is the idea, like we have very small points inside, like the times are very close, but they're discrete. Okay, they're discrete. So we'll understand what exactly is the mathematics behind it. So in mathematical terms, x1 dot dot xn follows like our random variables. Okay, are mathematically called random variables in probabilistic term. And yeah, so time series, actually time series, this idea of time series actually xt, this set of random variables, this set of variables, like, is actually called a stochastic process. So you can apply time series analysis, the stochastic process mathematics to time series analysis. Okay, so this is a basic mathematical definition and logical definition of time series, that it's a set of variables which are varying over time, where the 1 2 3 dot, this sequence matters. Okay, because that is the time. So this is the basic of time series analysis, and like the what is exactly time series. So the next thing I will discuss is that what is the main aim of time series analysis. So you will understand, as you will go through a lot of data of time series analysis, you can understand that there is a trend over there in time series, like this, a basic trend, and there is an error like this. Let me draw with some other color. Let's see if I see other color. Let's draw it. This is the error part, the extra error part. So if you just draw it, if you just remove the trend, you will maybe get like something like this. Something like this. But if you go on understanding, there is itself a pattern inside it. That is the pattern. Another pattern is called seasonality. What is seasonality? Seasonality is something that it occurs, the high occurs every single, you understand, this high occurs, this high occurs, this high occurs every single alternate amount of time. So this is called seasonality, and this seasonality is really important, maybe to understand, to capture. Okay, so we learn how to capture the seasonality, how to capture the trend, and the rest part that is left is called error. Okay, so this is the basic of time series analysis. So the main aim of time series analysis, the mathematics, the main aim of time series analysis is the following. Now, okay, so yeah, the main aim is that first of all we have to measure the trend. So like to understand the whole thing out there, and then main aim is understand the dependence among the data points. Okay, we'll go to that one, how time series different from regression. So in regression, time series, the data points are actually independent. YIs are independent. Okay, I will come to that just after this. So the forecasting is the main aim of time series, and also we are trying to understand how the cyclicity, the seasonal thing occurs at which rate. So we'll learn that how we can learn, like I will give an idea on how we can actually learn about that seasonality in the future. Okay, so that is the main idea of like we have a trend, we have an error, and we have a seasonality. Seasonality के लिए एक stuff, trend के लिए एक stuff, and then we will understand the error. So the main part is understanding the error, okay, because they are dependent over here. So that is the idea of time series. This is the main difference. I will share it again. So in a regression framework, if you kind of recapitulate, yi is equal to f of xi plus epsilon I. Now epsilon I follows actually iid something. Iid is error 0 and some sigma square, or some so error 0 and they behave similarly, even if not similar distribution, but they are independent of one another. But in time series they are not independent of one another. You can understand there is a cyclicity, there is a seasonality, there is a idea of dependence upon the previous day. Okay, so there is some dependence that we can actually understand. So how to model this? So this is a essential difference. So this epsilon I, this is called white noise. In time series also it's called white noise. So we cannot, like, this will come, this is random fluctuation. Okay, we cannot avoid that. That's why we are studying statistics and probability. So I remember a quote where one of my professors told that white, like, the error is the living like livelihood, understanding error is the livelihood of a statistician. Okay, so yeah, so without errors we cannot work. And then what comes up is that we have this error. So in time series what is happening is that they're dependent upon one another. The errors are dependent upon one another, and which will continue like to assume, and therefore we cannot apply the usual regression techniques on time series. So we need to, so the main aim focuses, therefore we can easily now capture this by usual regression trend. This is a trend. Okay, this is a trend. But the external part, after detrending the whole thing, we have seen something over here that I drew. So that has seasonality and that has error. So how to capture that? That is also a really important aspect. And we'll see how to capture that, because understanding that is the main focus of time series, not this f of xi. So f of xi you can easily calculate by the normal methods. But understanding, there are other easy methods, smoothing and various easy stuff. Okay, we'll understand what the methods, but the main aim is understanding the errors in time series where they are dependent upon one another. Okay, after retraining that. And let's go ahead and see what is there. So this is how time series is different from usual regression. And then how to mathematically model time series. Therefore comes the next question. The mathematical modeling of time series comes up in this way. So we need the first white noise that I told, that yt, that yi follows 0 comma sigma w square. Then iid. Okay, this is something like it's a random fluctuation. We cannot avoid that. And you can understand, if we draw, just take a white noise over time. If you just simulate y1, y2 dot yn, and simulate its y500 till y500, you just plot it, it will look like just white noise. Okay, it will look like just white noise. And the errors can hurt if the errors are white noise. If the errors are white noise in a time series, then we can apply the usual regression framework by OLS or maximum likelihood estimate or whatever we know. Okay, to estimate the trend, and then we can predict it, just like we use the regression framework. Okay, that's the basic idea. if the all the errors is all the errors are white noise, then we can use the usual regression framework, but that we will not do over here. Let's see. So as I told, there's a trend aspect. Let's take this data. So it's like chicken price data, I guess, over here, and the chicken price data is this. No. There's a trend. You can see the trend. Okay, it's a linear trend. You can understand that. So maybe you can try to model it by xt is equal to beta naught plus beta 1t plus epsilon t. As I will tell you, epsilon t is actually related to each other. I will show you why. Now, as I told, the main aim of time series is not understanding the trend. Understanding the trend is a part of it, but it's forecasting and maybe how to, like, I will tell you how to understand the dependence of the errors. I'm telling it over and over again because it's the most important part. So let's say we have understood the trend and we need to subtract. If we have understood the trend, we have modeled the trend, and what we can do is that we need to understand the error structure. Okay, so let's say we detrained it. So the relationship can be actually super complex. I can tell you that maybe one time series depend upon other time series. Okay, one time series can depend upon other time series actually, and the relationship can be super weird. Okay, there is a time series called this where xt is equal to mu plus xt minus 1 plus something plus, it's like the basic time series is this. There is a mean curve, that is trend curve. X is equal to mu t plus epsilon t. This is a like what you know about the. So let's say this is a white noise. Now this epsilon t is actually can be again like probabilistic in nature. So xt can be is equal to the epsilon t can be is equal to epsilon t minus 1 some another random error with some properties which is called stationarity. I will come to that, plus some delta. So this is called drifted random walk. So this is not an important idea, but what I am telling you is that why I told you is that this can be really complex behavior. Okay, they're very complex models. So what is the general algorithm to do it? What is the general algorithm to do? That's what we'll understand. Okay, so I will come to that step by step. Now understand the trend and seasonality of the days, and then detrending of the time series. As you can understand, if you just detrend it now, I will show you the picture. I've drawn it already. So if you detrend it, so you get that xt is equal to this was the initial condition. Then you detrend it. Why? Like detrending when you will delete the trend. Okay, how can you do it? We can do it in this way, that we are deleting the linear equation and we get this diagram. But you can understand there is a high every, I think around every 10 years there is a high, or 5 years there is a high. Okay, I mean there is a seasonality over here. So we have not captured or deleted that. So how to delete that? So how to understand that? We also need to delete the seasonality, because seasonality is not a good error. Seasonality has some pattern. Error is sort of should be random stuff. So seasonality should be also deleted. So there is something called detraining by differencing. So what we do is that understand that if we difference it down, xt is equal to yt. We differentiate because you understand that if yt is equal to say some linear equation plus some epsilon t, this can be, if you differentiate, the linearity will go, right? The linearity will go, and therefore what we will get is that we will get this equation. We will understand yt now, beta naught beta 1 plus epsilon t minus epsilon t minus 1. Now this is a really beautiful idea. This is a really beautiful idea, and now we can understand it. Let's draw it up. And understand that this is the first difference, and you can understand the mean is actually around this 0.0. Mean is actually 0 or maybe a bit above 0. So you can understand beta 1 from here. Actually, you can understand beta 1 from here. The mean of this first difference, and mean of this first difference, and yeah, then we can model it. Okay, then we can model this. But this, understand, these are still dependent. The errors are still dependent upon each other now. So we need to model therefore the error. So what we are doing first, understand, we are first detrending the whole time series there. So also understand that we have removed, there is no really a good pattern of this always like up and downs really in a random framework. So the seasonality is also being deleted over here. Minus seasonality, minus trend. So what we are left with is actually the error. Okay, but this has some pattern inside there. This is not random error, because you can understand the random error looks like this. It is totally random, but this is not random error. There is some pattern over here because there is this dependence upon here. So there is some dependence upon here. So we'll understand the dependence. So the first step is that the first step in time series is there. So first step is that you need to detrain the time series, difference or detrain. That is usually done by differencing methods. I will tell you in details what are the key, how to do it, and then we get difference also removes the seasonality in some sense, and then we understand the errors ka dependence. That is the main aim. Once we understand the error ka difference, we can actually predict it whether it will go up or down. Okay, in that sense, suppose the errors are positively correlated, okay, or negatively correlated. Like if some error is positive, the next error will likely be negative, and then since it's negative, it will be positive again. Since the errors are negatively correlated, so therefore, if it's going down here, we can predict that maybe it's going up in the next one. Okay, that's the idea. That's the main idea, guys. That's the main idea, and that's a very simple idea actually. So this is a way we can actually understand the structure, the relationship between the errors that we know. So this is the way we should understand the trend and then seasonality and then retrain the seasonality, because the main aim focus is that if you go is to understand a dependence upon the random variable. And dependence exists in the errors only. Okay? So the main aim is focusing on the understanding the dependence of the error, and by understanding the trend and removing the trend. Okay. This removing the trend, it actually you will understand this differencing is actually what is the I of in ARIMA model. Okay. You will learn about this, the I of ARIMA modeling. This I. And AR and AMA, I will share it with you. It's understanding the dependent structure of the errors. Okay, coming to that, let's understand. Therefore, we have understood, therefore, that after determining the whole time series, we are interested with the left with the residual sample errors, which have a good dependent structure, and we must have some good, and they must have some good properties. We'll explore the properties, which we will explore now. Okay, perfect. So this is a perfect point to understand the whole thing, and this is where the next climax is coming up. So understand that we will now go on to understand the dependence errors, different structure of the errors of the data points, unlike regression, which was not done in regression. So to understand dependence, we have something really in our arsenal. It's covariance. So what we do, our data, if there is xt, this time point over here, and this is xt and this is xs, we can understand how these two data points are related by taking the covariance of it. And that's a beautiful idea. We will take the covariance of it. Oops. Just give me a moment. Yeah. We'll take the covariance of it to understand so this will give an idea whether it's the two data points at that time s, t and s are correlated or not. That's a perfect understanding of dependence. That's we all know, right? Covariance is the basic idea. But covariance can be really, really high. Covariance can be really, really high in magnitude, okay? So we need to normalize it. So the way of normalizing is autocorrelation function. Just we take, instead of covariance, we take the correlation, so that we know that the correlation can be between 0 and -1. Sorry, 1 and -1. By Cauchy-Squartz inequality, you can prove that. And it measures a normalized dependence. SCF measures, is called ACF, lovingly. ACF measures the normalized dependence with the two data, so that we can measure it for two different time points actually. Let's say x1 and x3, while on x5 and x8. We can measure the time, or we can measure the dependence upon this. But you may ask that how to measure it. Like we don't know the actual row, the actual thing. So that's where the estimation comes up, statistics part comes up, that we need to estimate it using statistical methods. Usually we can understand the correlation by using by using the sample correlation, okay? That's the idea. Let's say you are understanding x row of. Okay, let's go ahead. We will understand not this, but let's understand what we can do in a generalized, in a easy case where we will understand in a good property case. So this is like how we measure the dependence. But understand this very carefully. If the errors behave very randomly, like this, very, very weirdly, that x1 and x3 are not. So suppose we want to understand the behavior with x1 and x3. Okay. row of 1 comma 3. Now understand, we have only one data point. How we can do that? We cannot do that. So we need some good properties of the time series data, the errors, the properties of the errors, which we will impose upon, so that we can estimate this row, this correlation, the dependent structure. So our main focus is now to understand the dependent structure. So understand to understand 1 comma row of 1 comma 3 is really how we have one data. We cannot calculate SD. We cannot calculate. Maybe we can calculate that. We can we cannot calculate covariance of x1 comma x3 because we have only one data point. That's very weird. We cannot calculate that. That's not a good thing. So we need to have a lot of sample to understand this. So how to do this? That's the main idea, and that's where comes up the stationarity idea of the time series data and actually the errors in some sense. I will share with you. So the one idea of time to understand the autocorrelation function, in a good case of autocorrelation function means that there's a dependence upon time one and let's say time t and time s. So I will tell you why this means, but before coming to this, we must understand that. Okay, let's understand this. So autocorrelation function. Before this, we must understand something called stationarity. To understand stationarity, guys, this is called a good predictable errors must be stationary. Why? As I told, that the stationarity gives an idea of similarity, like stationarity in the probabilistic framework. Why? It means that the time point, say, let's say it's telling that if time point x1, x3, and x5 will behave similarly at x200, x202, and x204. What it means is that if the difference of the time length, x200, x204, so that means that this set of time, how they're related, how they're correlated, how they're behaving is actually similar, even if we take a set of time data points at a time, say at some time points at some intervals, if we just shift it to some other place, it will also behave the same because it's error. That's what we can assume. The error can behave the same way, not the trend. Understand this. The errors can behave the same way. So we need this probabilistic condition, this idea of good predictable errors, because if we don't have that, why is this helpful? Let me understand that. Why is this helpful? Let's say if x1 and x3 therefore is behaving similarly, like x11, x3.1, x1.2, x3.2, karte, let's say x10, x12. So if we have this, guys, if we have this lot of data now if we try to understand how x1 and x3 is behaving, we can take all this data because they are behaving the same way, and then take the average. We can take the correlation of we can take the covariance. We can find out the sample correlation now of this sample. So what is happening? We can actually predict the difference. We can actually estimate the difference, a covariance dependent structure, not the difference, the dependent structure of the x1, x2, x1, x3, because we have a lot of data points similarly behaving like that. Otherwise, you cannot estimate, right? And that's the solution to this. We will assume it's stationarity, and also it's a good assumption, But this extreme stationarity that they are behaving exactly the same manner will not hold. So what we will learn is that we will understand something called weakly stationary, where we will only understand, we will take two conditions, that the mean value is actually behaving similarly over time, and just give me 1 second. The mean value actually is behaving similarly over time, and so why it's true? Because if you take the condition that x1, x2, or xn all are behaving in a stationary framework, then the mean will remain constant over time. The expectation will remain constant over time because x1 is similarly behaving, x2 is similarly behaving as x3. The single sequence, single data points are similarly behaving, so the mean must remain constant. The mean must remain constant. That's a really important idea. Now there is something called autocovariance. As I told, now autocovariance also remain constant because we have understood that the pairwise, the set of the random variables must also behave constantly. Must be behaving same. This collection of random variables must be behaving same with shifted time. So the autocovariance, which is the relationship between x1 and xt and xs, must also be behaving same because xt and xs must similarly behave as xt plus h and xs plus h. And this coming to this idea, this two are behaving same. Therefore, their autocorrelation of this is behaving same also. This is same as actually this, because they are behaving same. So therefore, understand it's true for all eights, right? So essentially, autocorrelation now boils down to something called ACF of H, because we are not dependent upon two time points now. We only depend upon the difference. Only difference matters. It's only difference matters, because for every difference we have a sequence of all the time points. They are behaving in the same manner. So what we'll study now, that assuming this good property of the errors, what we'll study now is that we will study ACF of H. And this is actually good, because we have something in terms of sample. To understand ACF of 1, what we'll do, we'll collect data points of x1, x2, x1.1, x1 2.1. करते करते जितना data points है, one difference का. We'll take the auto correlation, the sample correlation of that, and we'll estimate ACF of H by that. That's how it's done. Now, understand that the mean is remaining constant. We have understood why the mean is remaining constant. And if the mean is remaining constant, if we consider the trend, okay, the trend is not actually, if you consider this trend, how this is behaving, the trend is actually not a stationary condition, because if time is a trend, then it is not stationary, because the mean is changing. So we need to detrend that to get to stationary, to get the errors, the time points of the error, stationary value, the idea of the errors. But the error can be having a simple mu, a simple constant. So what we will do, that we will actually delete that. I believe that after detrending also the mean gets deleted. So therefore we have the errors, which is actually mean 0, and it's stationary. So errors are mean 0 and stationary, which also consider the dependence structure. Perfect. So in the meantime, I've also discussed why the condition of the stationary, guys. Why do we need the stationary condition? Okay, because it helps us estimate the difference, this dependence structure, and we have what? We are measuring the dependence structure by ACF of H now. Okay, and let's see something good properties I told for this data point. So for this, let's forget the word moving average. For this data point, the ACF function is like this. It's a stationary, you can sort of show it. So ACF function is like this. Understand that ACF function is what is minus 22. It's called a lag. H is equal to t minus s. It can be lag, okay? In fact, we take the modulus of it. If you mathematically calculate this, it will turn out ACF function will turn out actually of H, be turning out like, if the variance of the white noise is somewhat, it will be like 3 by 9, 2 by 9, and something less, something maybe 0 then, as H is greater than 2 or 3. So something like this, okay? That means it's decreasing over time. What does it mean? It's a really important aspect. It means that as time goes, the dependence upon the, so what is ACF of H? It estimates what? It estimates the difference of, let's say, ACF of 4. It calculates the dependence of x1 and x5, x2 and x6. So all these sample points, all these data points. So what it calculates how they are correlated. See, if it is low, it means what? If it's turning out to be very low, it means that actually the dependence is gradually decreasing over time. So ACF function is measuring the dependence. The dependence actually gradually decreasing over time. This is the dependence. This is how high is the dependence, okay? So the next, zero lag is really dependent, because why zero lag is dependent? Because that's the variance of the 2 points of the point. Then the 1 lag, it's a slightly dependent, and then 2 lags, and then after 3 lags, it's going towards 0. That means what? That means the dependence is decreasing over time. That's very natural. For good time series, the dependence must decrease over time. If a time point is now, if something is dependent thousands years from now, we cannot really predict that. Okay, I mean, that's a really hard thing to do. Okay, so I mean, this is a really hard thing to do also, and understand this. So therefore, for good predictable errors of time series and understanding the dependence structure, we need this stationary condition, which leads to this ACF function, which is really important to understand how the difference is. So to understand the dependence, how the dependence is, to understand the dependence, therefore we need the ACF function. We need to calculate the sample ACF function when we can understand the dependence, right? This is a basic idea, guys. So we understood. So therefore I'll discuss the steps once again. So why we need it? As I have told, we need The dependence structure now to understand the dependence structure, we have two models. There is AR model and MA model. This auto-regressive model and this is moving average model. So this is the understanding dependence of the errors. Okay, so the stationary condition really helps in in calculating that. So what is the central idea? This is a final idea. The central idea is this, that we have time series equal to trend plus seasonality plus dependent error. We need to first convert the data into stationary data. Trend is not a stationary, seasonary is also stationary in some sense. No, seasonary actually can be included in the stationary, but trend is at all not stationary because the trend is actually something which is changing over time. Seasonality maybe not be changing. It's like sort of the average is same. So therefore, the idea is that, I mean, there are exact examples of seasonal data which are stationary. Okay, so understand. We have discussed about how to transform data into stationary data. So understand how we transformed in that case, in the previous case, guys. If you remember how we transformed, then we transferred it by detrending, by differencing, right? We understood the differencing is good because it also deletes the stationary idea, so that we can directly go into the errors part. So understand, if something is quadratic, if xt is equal to quadratic, say beta naught plus beta 1 t plus beta naught 2 t square plus epsilon t, which is dependent error, if we difference it two times, we will get something really common, really constant plus the error relationship. So what we are understanding, differencing it actually removes the trend in some sense, removes polynomial trends. So we can differentiate towards the degree of the towards the degree of the we differentiate d degree. Suppose the polynomial degree is the d, then we can differentiate d times to get the error, the stationary data. Okay, with the addition of mean, we can subtract it again. So we can, these are basic ideas. So we can detrend it by using differencing if it's a polynomial way. Okay, and the smoothing, the kernel smoothing, and this works actually in the polynomial framework, so it can actually help. So now understand if it's exponential, guys. What if it's exponential? What happens in exponential? If it's exponential, guys, if the data is like this, e to the power x t is equal to e to the power t into epsilon t, essentially what happens in exponential, it happens in growth, okay, GDP growth or whatever growth. It happens actually. And that sense, actually, the data is actually the variance also increases over time. We can also see that. I can give you data of that. So what we do, we do nonlinear transform using by log or power transform method. That is actually the Box-Cox transformation. So it's like it's actually behaving in a power fashion. It's like moving in a power way, like it's an exponential or it's moving in a power framework. Like we can do it by transforming, transforming powers. Okay, like power transforming means either is a Box-Cox transformation. You can use this. Okay, why we use this? Because we want to get this format, the trend format, this trend plus seasoning. We can want to get in an additive model. Okay, why we want an additive model? Because upon getting an additive model, we can detrend it by differencing, because we want to get the dependence error. So this is the basic idea. We can detrend it by differencing. So the first idea is we can difference, in case of polynomial trend, we can difference many times of retrend. Then we can see the data and we can do some experimental data analysis on this data to understand whether it's we need to linearly transform or not. We'll do that in a different video, but we need to do that. Okay, how to do that? We need to do that in a different video or different post. I will do that, but we need to nonlinear transform the whole polynomial trend. Okay, and then difference it to get why we focusing on differencing, so that we can get the dependent error. Okay, that's why we can get a stationary data out there. Upon getting the stationary data, we can actually estimate the SCF function. When we can estimate the SCF function, we can actually get we can use models to get the idea of AR and the autoregressive and moving average model. Okay, the good model to understand the dependence structure. So we can also understand the trend by using a smoothing method by another estimator, another Cullinan smoothing estimator. We can also detrend by that, and then we are do it like maybe it's a very hard function to understand, so maybe it's not working. In that case, we focus on this. So how do we do that? We actually focus on some statistical methods, and we can understand it graphically. Exploiter EDA is very important over here to understand whether it's a non-stationary data or stationary data. So first idea is we have to transform it into stationary data. The usual keywords over here is differencing. We can nonlinear transform into a polynomial trend. and then difference it to get the stationary time series, okay, the stationary data. So how we can understand, after you can maybe question that after transferring to stationary data, how we can get back the actual data, how we can predict it actually by getting an so we get the first we detrained it by transforming into stationary data, and then we understand by predicting the stationary errors, and then we get back using the same steps one by one by adding up those errors, okay, by adding up what we deleted to get the actual thing. And there are very easy models on this, guys, to implement also in R and Python, so don't need to worry about that, but understanding the theory behind this is really really important. Okay, perfect. So now understand that, so this is the way we need to transfer into stationary data so that we can use the data to sample data to estimate the ACF function to get ahead to the moving average and AR method, okay, to estimate the dependent structure. The next step is model and predict the dependent structure, which we do by AR and MA, which we'll discuss in details in the next post and the video. And this is really important. So this is the steps, guys. So we are all the steps are important, and you should follow the steps step by step as I told. And this theory is really important to understand. So that dependent structure, this idea of differencing, this idea is actually the I step. So what is ARIMA model in short for you? As I have this idea of transforming data into stationary data by transforming and differencing is the I method. It's integrated, and this I and this AR and MA is actually understanding the dependent structure and prediction of the errors, the stationary errors. Okay, so that's the idea, guys. That's the idea, and that's ARIMA for you guys. And we will understand ARIMA, ARMA, AR, MA, and ARIMA in a different video, and I will write a post on it. Till then, stay tuned and stay blessed. And I hope you enjoy the video. And I hope you enjoy the video, and if you like it, please do subscribe and share with your friends and people who really enjoyed it, guys. And so see you in the next video, and stay tuned and stay blessed. And if you have not subscribed, do subscribe to our channel.